The last math topic we will review before we get to the actual subject of this course, electromagnetics, is differentials. In this course, we will do integration over lines, surfaces, and volumes. So we'll need to have differentials, a line differential, a surface differential, and a volume differential in all three of our coordinate systems. Let's start with Cartesian coordinates, which you should already be pretty familiar with. Let's go to a point in Cartesian coordinates, x, y, and z, and let's increase each coordinate by a differential amount to x plus dx, y plus dy, z plus dz. Looking at our differential cube, you should be able to tell that this first point is at point S on the cube, and that we go to point B. Going from x to x plus dx, we can define a vector of magnitude dx in the x direction. Then going from y to y plus dy, we can define another vector, dy, in the y direction. Going from z to z plus dz, we can define another vector of length dz in the z direction. Our differential length will be the vector that points from our starting point at S to our final point at B, and it will just be the vector sum of these three differential vectors. So our differential volume will just be the volume of this differential cube. So the differential volume is equal to dx, dy, dz. We're going to have three differential surfaces, and we're going to define these as vectors. The directions of our differential surfaces will be the unit vectors that are normal to those differential surfaces. Here is our unit vector in the x direction, and the differential surface it is perpendicular to is this one of area dy dz. So here is our differential surface d sub sx. Here is our unit vector in the y direction, so this is the differential surface perpendicular to it, and it is of area dx times dz. Here is the unit vector in the z direction, so the surface it's perpendicular to is this one, which has area dx times dy. So here are our differential surfaces for the Cartesian coordinate system. The reason we treat differential surfaces as vectors is that will be useful when we're trying to determine the amount of flux going through a surface. To qualitatively illustrate that, let's look at some uniform vector field as shown in this figure. The bottom part is looking edge on at the field, and the top part is as if you were looking from the right-hand edge, so the tips of the vector field are the dots in the upper figure. So here we have a differential surface where the outward normal is pointing out, so we have 4 dots of electric flux going through it. So in the bottom figure, that would be looking at the edge here. So you see electric flux going through it. Now we're going to take this differential surface and rotate it. The bottom part is going to come at you, and the top part is going to go into the page until this arrow that you see the tip of, you're going to see the edge of. And the same thing in the bottom figure. Now we see no electric flux goes through our differential surface. So when the direction of the differential surface is perpendicular to the vector field, none of the vector field goes through the differential surface. When the differential surface direction is in the direction of the vector field, you have the maximum of the vector field going through the differential surface. From here to here, we rotated our differential surface 90 degrees. Let's now rotate it at some angle less than 90 degrees. So the bottom edge comes out towards you, the top edge goes away from you, and we stop, say, at something like a 45-degree rotation. So now we see that less of the vector field will go through our differential surface. Later we will see the dot product between our differential surface and the vector field will play a role in helping us determine how much flux goes through the differential surfaces. Now let's find the differentials for the cylindrical coordinate system. We'll start at point rho phi z and increase each one of our coordinates by a differential amount. So looking at the differential cube that's formed, we see that our starting point will be point R here, and our finishing point is going to be point A here. So when rho changes by a differential amount, we will trace out this vector pointing from R to Q. Its length will be d sub rho, and it will be in the rho direction. Now when phi changes from phi to phi plus d phi, we will sweep out this arc, and that arc length will be of length rho d phi in the phi direction. Here is a view looking down on the top. So point R here is at this point with component value rho, and point Q here is at this point with component value rho plus d rho. So when phi changes by an amount d phi, we sweep out an arc length. So this arc length here is really our radius, rho plus d rho, times the angle we're sweeping in radians, d phi. So here is this arc length, rho plus d rho times d phi. And because we get to our differentials by letting, say, delta phi and delta rho goes to 0, here we have two quantities that are going to 0 times each other, so we can essentially ignore this second term compared to the first term. And that's why I said that this arc length right here is of length rho d phi in the phi direction. And when z changes from z to z plus dz, we move from b to a. So let's define this differential length of magnitude dz in the z direction. So our length differential dl is the vector that's going to point from R to A, so it will just be the vector sum of these three differentials. So here is our differential length in cylindrical coordinates. As we go to differentials and this box gets to differential size, we can essentially treat it as a cube, so the differential volume will just be the product of the three sides. So our differential volume in cylindrical coordinates is rho d phi dz. We will again have three differential surfaces. The d sub s rho surface will be perpendicular to the rho direction. The d sub s phi differential surface will be perpendicular to the phi direction. And the d sub s z differential surface will be perpendicular to the z direction. Here is the unit vector in the rho direction, and the surface it is perpendicular to is A, B, Q, C. And this surface has area rho d phi dz. Here is the unit vector in the phi direction, and the surface it is perpendicular to is A, B, C, D. And that surface has area d rho dz. Here is the unit vector in the z direction, and it is perpendicular to the surface ACSD. And that surface has area d rho d phi. We will now find the differentials for the spherical coordinate system. This figure in the notes is a better one for visualizing what's going on than the one in your textbook. We will start at this point here. If we change r by an amount dr, we can define this vector right here of length dr in the r direction. If we change theta by an amount d theta, we will sweep out an arc length of r d theta, so we can define a vector of length r d theta in the theta direction. The one that's difficult to visualize is what happens when you change phi by an amount d phi. So we will sweep out this arc length right here, and that length is r sine of theta d phi. So we can define this vector of length r sine of theta d phi in the phi direction. To help visualize this arc length, let's look at the phi plane. Here is our plane at phi, and we know one end is always attached to the z-axis, and phi is the angle the plane makes with the x-axis. Now we will increase phi by an amount d phi. So this plane will move from here to this second dashed line here. When we change phi, we're not sweeping at a radius of r, but we're sweeping at a radius of rho. This length and this length are both rho of our cylindrical coordinate system. If you look at this right triangle, the hypotenuse is r, so this length here will be r times the sine of theta. Our differential length will just be the vector sum of these three vectors. The differential volume will just be the volume of this cube, which is the product of dr, r d theta, r sine of theta d phi. We will have three differential surfaces, one perpendicular to the a sub r direction, one perpendicular to the a sub theta direction, and one perpendicular to the a sub phi direction. Here's our unit vector in the r direction, so this surface area is r d theta times r sine of theta d phi. Here's our unit vector in the theta direction, so this surface area will be dr times r sine of theta d phi. Here's our unit vector in the phi direction, so this surface here will have area dr r d theta.